In this video I want to introduce structs by example. The main focus will be on using structs, but I also want to give you an idea what it means that with structs you can define your own data type, a user-defined data type. But let's just consider this example. Up here I declare a new type, a type foo with an uppercase F. And we will later say that this type foo has three members, A, B, and C, and each of these members has the type int. Now what that means becomes clear when we actually use this type in a definition of a variable, like for example here in function main. So this is the name of the local variable, foo with a lowercase f, and this is the type, foo with an uppercase f. So here we are using this type that we declared above. Now when we have a variable, we have a memory location which will be used for this variable. In this case, because it's a local variable, this memory location gets allocated when we enter function main. But that means when we entered function main, let's say this memory block will be used for foo. And now we can look into the details. We specified foo as having three members, each of them with the same type, a type int. And that means that this variable foo actually has three components. And when we talk about the struct, these components are called members. But this is just a convention. You will see that it's very similar in this case to arrays, where the convention would be that components are called elements. Let's talk about that later. Now the first component, the first member, is member A, and we can refer to this memory location by foo.a. So this is the memory location, the part of foo which belongs to member A. And similar, this would be the memory location for foo.b and this for foo.c. So you can refer to these components by using the name of the struct variable foo, append a dot, and the member name. That's it. And then you see here, for example, I assign values to these members, and that means I assign values to the corresponding memory locations. For example, here I assign the 42 to this memory location. So maybe I should write this in black so that it's easier to see. And here 13, and here 123. The same way I can access values for reading it, of course, and you see that here things are really very similar to arrays. Assume that here we would have declared foo as an array with three ints, like that. Local foo is an array with three elements of type int. Then we would have in memory a memory location for foo as before. And this variable would have these three components: foo with index 0, foo with index 1, foo with index 2. And then of course here you would instead assign to foo bracket 0 the value 42 and so on. And similar here you would also use an index. So you see that if you have a struct variable where each member has the same type, then technically a struct variable is similar to a corresponding array variable. Technically. For the use case, it's a bit different. I mean, here you can use names to access these components, and here you can use an index. Now in this video, I don't want to talk about when to use structs and when to use arrays. It's about getting into touch with structs. So let's first go over a few things that might be interesting when you deal with structs. The first thing is that if you have members, like before, of the same type, that follow each other in memory, then you also can write this in one line. The compiler treats this as if you would have written the code before, where A was declared to have type int, also B, and so on. So no big deal. You also can define initialized variables of a struct type. You can use the initializer list similar to how you can use initializer lists for arrays or other variables. You specify here basically the initial value for each member. So this is the initial value for the first member, this here for the second member, and this here for the third member. You also can specify fewer initial values, and then the compiler will use a zero value for that. So check that out. If you would skip this here, then the output should be foo.c equals 0. And this is defined behavior. So it's not that here some random value will be used. The compiler will insert for each missing initial value the value 0. Because the compiler knows that in total 3 members are in a variable of this type. So here I made a modification which results in a compiler error. Let's look into this modification, what changed, what was my intent here, and how can we overcome this problem. Before I had this initializer list in the definition of this variable. I had it up here. So here the initializer list was used for describing how a new variable should be initialized. Now technically this is different to what you see here, because here this variable already exists, and that means we have here an assignment. And in an assignment you basically have something like in physics where the units on the left and right hand side of the equal sign should be the same. So the type of foo should be the same as the type of this initializer list. And technically an initializer list doesn't have a type. Now this is actually something that ABC inherited from C and also C++. This initializer list is actually called a compound expression. I mean, this is not relevant, but relevant is that technically this expression with this curly parenthesis doesn't have an actual type. And that means you somehow compare here or assign apples to potatoes or apples to oranges or whatever. But of course, we would expect that a compiler treats this as if you would have written foo.a equals 42, foo.b equals 13, foo.c equals 123. And technically it would not be difficult to actually have this, that the compiler is treating it equivalently. So the compiler could generate code from it. But here I somehow made the decision that I somehow have to prepare you for C and C++, where this would not be allowed. So to overcome that, you basically have to give this initializer list or this compound expression, this expression with the curly parenthesis, explicitly a type. And you can do this. You simply have to specify in front of the initializer list with an explicit cast a type for the initializer list. Then the right hand side and the left hand side have the same type, the same units, and then this assignment is val post. If you're interested in what the compiler is generating from this line of code, how the compiler is treating this assignment, I actually can tell you the ABC compiler generates from that first a local variable with some internally given name. Let's call it internal. And the type of this internal variable is what you specify here. And this variable gets initialized with this initializer list. So with 42, 13, 123. And then it also generates an assignment. Foo gets assigned the value of this internal variable. And if you're now worried that something like that is inefficient because you generate additional variables, don't worry. The optimizer will easily turn this then into foo.a gets assigned the value 42, foo.b gets assigned the value 13, and so on. So there will be no runtime overhead if you turn on some mild optimizations. Now, what you see here, by the way, is also that compilers basically just generate code, and from this code, more code. So if you have something like that with a rule that you have this explicit initializer, then it's very simple to write compilers for that. And maybe that's also the reason why something like that is required for C and C++. By the way, there is another option to achieve the same. You see here, basically I have the same as before, just without this round parenthesis. The reason for that is that I have here something which helps me to prepare you for C++, maybe one day. This here basically is a form where you would say in C++, foo with this uppercase F is the name of a class, and here we have in this curly parenthesis arguments for the constructor of this class. And then it means you generate here on the right hand side a new object of this type foo and assign it to this variable foo with a lowercase f. But technically it's the same, and whether you want to use this or with the explicit cast, this is up to you. Okay, so but that's it for this video, for the first contact with structs in ABC. In the next video I will show you a more interesting example, a struct where the members do not have the same type, where it actually makes more sense to use a struct